Hey guys, in this example, I'm going to show you how to do binomial distribution probability calculations in Excel. Okay, and this is what I would expect you to do for your homework and for the exams, is just use Excel as your calculator rather than use the complex formula to do these by hand. Go ahead and read the problem description that I have pasted here. Let's summarize real quick. This is a binomial distribution because we have a fixed number of trials or fixed sample. We took 8 tickets. Each ticket has 2 outcomes. It's either winning or not winning. There's a consistent probability of success, 35% for a winning ticket, and then each ticket is independent of the other. It has no effect on whether the next ticket wins or loses. Okay, so X follows a binomial distribution. N is 8. I copied that there. The probability of success, or the probability of a winning ticket, is 0.35. So to start this out, I'm going to show you kind of the long way. Let's build the entire distribution of X. Distribution, let's remember, tells us what values X takes on and how often it takes them on. X is the number of winning tickets out of 8 that are purchased. X is the number of winning tickets among the 8 that are purchased. So possible values that X could take on, we could buy the 8 tickets and 0 of them would be winning tickets. 1 of them could be winning ticket, 2, 3, so forth. How often do these values occur? That's where the probabilities come in. What's the probability of 0 winning tickets? What's the probability of 1 ticket? So to calculate this probability, we know that X is a binomial distribution or binomial variable. So in cell I-12, we want to calculate the probability that X is 0, that we have 0 winning tickets out of the 8. Or in probability statement form, probability that X equals 0. Okay, Excel has a function to do exactly this. It's called binom dist, or binomial distribution. I'll bring it up in its expanded form here, just so we can look at it easier. Number underscore S is the number of successes that I'm calculating. I'm calculating 0 successes. Trials is the total number of trials. You purchased a total of 8, so 0 out of 8. Probability underscore S is the probability of success, 0.35. Cumulative, we're going to go over this later. For now, this is a true or false argument. For now, we're going to put in false. Again, I'll go over that more later. Okay, 0.031864. So instead of going through this whole thing, plugging in 0 for X, 8 for N, and going through that, we can just use a quick calculation in Excel. Let's go ahead and finish out the whole distribution here. We use the same formula, binomial distribution. Number of successes. Instead of typing in the values, I'm going to now use the cells. So number of successes is 1, or that, what's in that cell. My total number of trials, 8. I'm going to lock this cell. Go ahead, I would suggest you do that too. Probability of success, 0.35. I'm also going to lock that cell. Again, that's hitting the F4 key to put dollar signs around it, and then say false. Click OK. Because I locked my N and my P cells, I can now just drag this across and quickly calculate the probabilities for all of those. So here's the entire probability distribution of X. Let's look at these probabilities here. Remember, for a probability distribution to be valid, all the probabilities of the sample space must sum up to 1, and they do. What's the probability that 3 of the tickets purchased are winning? What's the probability that X is the number of winning tickets equals 3? Well, we've calculated all the values and the probabilities for it, so the probability that X equals 3 is just the 0.2785. If we hadn't calculated the distribution over here, I would still just simply use the binomial distribution formula. Number of successes is 3 out of 8. Probability of success, and then false. Same thing. Okay, next question, B. What's the probability that 3 or fewer of the tickets purchased are winning. Let's do this in a probability statement. First, probability that the number of winning tickets is 3 or fewer, so less than or equal to 3. So let's first just think about the values that x can be. If it's less than or equal to 3, x can be 3, 2, 1, or 0. All of those are possible values. So to write this the long way, we can sum up the probability that x is equal to 3, 4, plus probability that x is equal to 2, plus probability that x is equal to 1, plus probability that x is equal to 0. To sum up all these probabilities, we're just going to sum up probability x is equal to 3 plus 2, 1, 0. A much easier way to do this is, let's go back to our binom.dist formula. Number of successes. I still want 3 or fewer. The number of trials still is 8. Probability of success, that doesn't change. Now, here's where we want to look at this cumulative true or false. So far we've been doing false, that we don't want a cumulative probability. We just want the probability associated with whatever number we put in for our success. If I do true, which in this case I'm going to do true, the cumulative probability means it's going to accumulate all the probabilities at this x value all the way down to the bottom of the distribution. Same answer as what we got there. So again, if I put true in, it starts at the value that I put in for my number of successes, which was 3, and it's going to sum up all of those probabilities for me. Part C, probability that more than 5 of the tickets purchased are winning. First step, let's put this in a probability statement. The probability that the number of winning tickets is more than 5. So x greater than 5. Again, this is kind of the long way to think about this, but I'm going to go through it. X, according to this probability statement, x can be 6, 7, or 8. Okay? All those x numbers are greater than 5. Notice strictly greater than 5, not greater than or equal to 5. So same long way again, but we can just sum up the probability that x is equal to 6 plus x equal to 7 plus x equal to 8. Which is the same thing as just adding up the probability here, plus here, plus here. But there's a faster way to do this, again, using our binom.dist function. We have to be a little bit creative though. Number of successes, I see a 5 here, so I'm going to put in 5 there. My trials, same. Probability, same. Let's see what happens when we do a cumulative probability. We know if I put in false, it will return the probability just associated with 5. So it's going to return 0.08. 0.08. If I change this to true, that I do want a cumulative probability, that's going to return from 5, summing all the way down. It returns the sum of all those probabilities, 0.9746, 0.9746. I need 0.025381. I need the sum of all of these numbers. So this is where we get a little creative. I know the entire distribution is equal to 1. Sum. I have calculated with this statement here, this formula, these probabilities. But I want these probabilities. The entire distribution, again, is equal to 1. So if I take 1 and then I subtract out the yellow, all I'm left with is the blue. 1 minus the yellow probabilities will leave me with the blue probabilities, which is what I calculated earlier. This is the correct answer. 0.025 is the probability that x is greater than 5. Okay, last couple questions. We're going to calculate the expected number of winning tickets, or the mean of the winning tickets. The binomial distribution has its own formulas for the mean and variance. Okay, so we have to be very careful when calculating the expected number of the mean or the variance that we know what distribution we're calculating it for, because the formulas will vary from distribution to distribution. For a binomial distribution, the mean or the expected number is just n times p. So in part D, calculate the expected number of winning tickets. That's the same thing as asking what's the mean number of winning tickets. I just take n times p. Okay, 2.8 tickets. Okay, for the variance, number of winning tickets, just going to follow this formula for the binomial distribution. It is n times p times 1 minus p. 1.82 tickets squared. Whenever I calculate the variance, the units turn out to be squared. So it's not very easy to interpret tickets squared, or really anything squared. So we typically use the standard deviation. The standard deviation in any distribution is always just the square root of the variance. So simple, to calculate the standard deviation, I'm just going to take the square root of my variance, 1.34, and now my units are not squared anymore. It's just the original unit of measure, 1.34 tickets.